As an aside, we'd like to introduce you to a new language feature called conditional expressions, which can evaluate one of two sub-expressions depending on a Boolean value. They take the form result equals true value if condition, else false value. This syntax is perhaps surprising, with the condition being placed between the two possible result values, but it reads nicely as English and emphasizes the true value, which is usually the most common result. We can use it to simplify our sequence class function down to a single expression, obviating the need for the intermediate variable binding CLS and retaining the single point of return. Conditional expressions can be used any place a Python expression is expected. Their full syntax and somewhat tortured history is covered in PEP 308. Sometimes we want to be able to create a simple callable object, usually to pass directly to a function, without the bureaucratic overhead of the def statement and the code block it introduces. Indeed, in many cases it's not even necessary for the callable object to be bound to a name if we're passing it directly to a function. An anonymous function object would suffice. This is where the lambda construct comes into play, and used with care it can make for some expressive and concise code. However, as with comprehensions, excessive use of lambdas can serve to obfuscate rather than clarify code, running counter to the Pythonic principles which value readability so highly, so take care to deploy them wisely. If you're wondering why a technique for making callable objects from Python expressions is named after the 11th letter of the Greek alphabet, the origins go back to a foundational work in computing science in 1936 by Alonzo Church, predating electronic computers even. Church developed the lambda calculus, which forms the basis of the functional programming techniques used in languages such as Lisp. A good example of a Python function that expects a callable is the sorted built-in for sorting iterable series, which accepts an optional key argument, which must be a callable. For example, if we have a list of names in strings and we wish to sort them by second name, we need to pass a callable as the key argument of sorted, which will extract the second name. To do this, we can use a lambda to produce such a function without the bother of needing to think up a name for it. Let's create a list of scientist names: Marie Curie, Albert Einstein, Niels Bohr, Isaac Newton, Dmitry Mendeleev, Antoine Lavoisier, Carl Linnaeus, Alfred Wegener, and Charles Darwin. Now we'll produce a new list of sorted names using the sorted built-in and passing a lambda function as the key argument. Here our lambda accepts a single argument called name, and the body of the lambda, after the colon, calls the str.split method and returns the last element of the resulting sequence using negative indexing. Lambda is itself an expression which results in a callable object. We can see this by binding the result of the lambda expression to a named reference using assignment. We can see that the resulting object is a function, although it doesn't have a name, and that it is indeed callable like a function. Creating a callable function this way, using lambda and binding to a name through assignment, is equivalent to defining a regular function using def, like this. Let's spend a moment to point up the differences between lambdas on the one hand and regular functions or methods on the other. Def is a statement which defines a function and has the effect of binding it to a name. Lambda is an expression which returns a function object. Regular functions must be given a name, whereas lambdas are anonymous. The argument list for functions is delimited by parentheses and separated by commas. The argument list for lambdas is terminated by a colon and separated by commas. Lambda arguments are without enclosing parentheses. Versions of Python predating Python 3 have special handling of tuples using tuple unpacking in the argument list. This confusing feature has been removed from Python 3, so in Python 3 code there are never any parentheses between the lambda keyword and the colon after the argument list. Both regular functions and lambda support 0 or more arguments. A zero-argument function uses empty parentheses for the argument list, whereas a zero-argument lambda places the colon immediately following the lambda keyword. The body of a regular function is a block containing statements, whereas the body of a lambda is an expression to be evaluated, and the lambda body can contain only a single expression, no statements. Any return value from a regular function must be explicitly returned using the return statement. No return statement is needed, or indeed allowed, in the lambda body. The return value will be the value of the supplied expression. Unlike regular functions, there is no simple way to document a lambda with a docstring. Regular functions can easily be tested using external testing tools because they can be fetched by name. Most lambdas can't be tested in this way, simply because they're anonymous and can't be retrieved. This points the way to a guideline to keep your lambdas simple enough that they're obviously correct by inspection. To determine whether an object is callable, you can simply pass it to the built-in function callable, which returns true or false. So, as we have seen, regular functions are callable, such as this is-even function. Lambda expressions are callable, such as this expression which determines whether a number is odd. Class objects are callable because calling a class invokes the constructor. And methods are callable. We have also seen that instance objects can be made callable by defining the dunder-call method. Lest you get the impression that everything is callable, there are plenty of objects which aren't, such as string instances. We've already been using functions which support extended argument syntax, although you may not have realized it. For example, have you wondered how it's possible for print to accept 0, 1, 2, or in fact any number of arguments? Another example we've seen is the use of the str format method, which can accept arbitrary named arguments corresponding to the format placeholders in the string. In this section, we'll learn how to define functions, or more generally callables, which can accept arbitrary positional or keyword arguments. Let's start with positional arguments. Drawing an example from geometry, let's write a function which can return the area of a two-dimensional rectangle, the volume of a three-dimensional cuboid, or indeed the hypervolume of an n-dimensional hypercuboid. Such a function needs to accept an arbitrary number of numeric arguments and multiply them together. To do this, we use a special argument syntax where the argument name is prefixed with a single asterisk. Before we implement the computation, we'll simply print out the value of args and its type using the built-in type function. Notice that the asterisk does not form part of the argument name, and the argument name we have chosen here, args, is widely used in this case by convention, although is by no means necessary. Colloquially, this form is called *args. Now let's call our function a few times. We can see that args is passed as a tuple which contains the function arguments. Knowing this, it's a simple matter to write code to multiply all the values in the tuple together to get the result. Redefining hypervolume and using a more documentary name for the argument gives us this. The function works by obtaining an iterator I over the tuple and using the next built-in to retrieve the first value, which is used to initialize a variable v in which the final volume will be accumulated. We then use a for loop to continue iteration with the same iterator to deal with the remainder of the values. We can use the function to compute the areas of rectangles, the volumes of cuboids, and the hypervolumes of hypercuboids. It also generalizes nicely down to lower dimensions to give us the length of lines. However, if called with no arguments, the function raises stop iteration, exposing an implementation detail about which clients of our function should be unaware. There are a couple of approaches to fixing this. One change could be to wrap the call to next in a try except construct and translate the exception into something more meaningful for the caller, such as the type error that is usually raised when an insufficient number of arguments is passed to a function. We'll take a different approach of using a regular positional argument for the first length and the start args to soak up any further length arguments. Using this design, the function continues to work as expected when arguments are supplied, and raises a predictable type error exception when insufficient arguments are given. At the same time, the revised implementation is even simpler and easier to understand than the previous version, which used an iterator. When you need to accept a variable number of arguments with a positive lower bound, you should consider this practice of using regular position arguments for the required parameters and start args to deal with any extra arguments. The start arg syntax only collects positional arguments, and a complementary syntax is provided for handling keyword arguments. Let's look at that now. Arbitrary keyword arguments can be accepted by callables that use an argument prefixed by a double asterisk. Conventionally, this argument is called kwargs, although depending on your situation you may care to choose a more meaningful name. Let's make a function which returns a single HTML tag as a string. The first argument to the function will be a regular positional argument which will accept the tag name. This will be followed by the arbitrary keyword args construct, to which tag attributes can be passed. As before, we'll perform a simple experiment to determine how the keyword arguments are delivered, by printing the keyword args and the type of the keyword args. When we call the function with some suitable attributes to create an HTML image tag, like this, we can see that the arguments are transferred to our keyword arguments formal parameter as a regular Python dictionary, where each key is a string bearing the actual argument name. Note that as with any other Python dictionary, the ordering of the arguments is not preserved. Now we'll go ahead and implement our tag function properly using a more descriptive name than kwargs. Here we iterate over the names in the attributes dictionary, building up the result string as we go. It's worth pointing out at this stage that this strut format method we call here also uses the arbitrary keyword args technique to allow us to pass arbitrary named arguments corresponding to our replacement fields in the format string. This example also shows that it's quite possible to combine positional arguments and keyword arguments. In fact, the overall syntax is very powerful so long as we respect the order of the arguments we define. First, star args, if present, must always precede double star keyword args, so this isn't allowed. Second, any arguments preceding star args are taken to be regular positional arguments, as we saw in the hypervolume example earlier. Thirdly, any regular arguments after star args must be passed as mandatory keyword arguments. Failure to do so results in a type error. Fourthly and finally, we have the double star keyword args arbitrary keyword arguments, which if present must be last in the argument list. Any attempt to define an additional formal argument after double star keyword args results in a syntax error. You should take particular care when combining these language features with default arguments, which have their own ordering rules specifying that mandatory arguments must be specified before optional arguments at the call site. Before moving on, we should point out that all of the features of the extended formal argument syntax apply equally to regular functions, lambdas, and other callables,